So on that note, we're recording. So let's start. So we've covered 4 sessions, and today we're just going to go over a little bit lightly what we covered so far, and then I'm going to go through the steps that you have to follow to do a thorough logistic regression. I want to repeat that the way I do it isn't the only way to do it. Like if you find other sources online or papers that recommend other directions, that's fine too, and in particular around the diagnostics. So there are hundreds, well, scores of ways of doing diagnostics, test of significance, testing out your model. The ones I've showed you are, I think, the easiest ways, and probably well beyond what's expected in this master's program. So it's a safe thing to do. Most people run these regressions in this program and just present the results, and there isn't a lot of expertise amongst the professors to interrogate the level of detail you've gone into. But if you really want to be, impressive, you can go more deeply and look up more complicated stats methodologies. But let's review. First thing we're reviewing is, what is it? Hopefully you all understand what it is now. It's this logic thing where we have a set of explanatory variables that are modeled towards a dichotomous outcome. I know you know this, but it's amazing, as I'll talk to each one of you about your project going forwards and all your committees, I think, we're going to find, oh, you've got a third level to your outcome variable there. What's that all about? So that's key. That's the first thing, is that your outcome variable must be yes or no, 1 or 0, 1 or 2, present, absent, on or off. It's got to be binary, binary, binary. And you must be clear in your head which one codes for which and which one you care about. The one you care about is the higher number. What does that mean? Let's say your outcome is, like in your case, HIV presence, right? So the higher number has to be HIV positive. So 1 means positive, 0 means absent. Or 2 means positive, and 1 means absent. Because that's what the computer sees it. The computer doesn't know what HIV is. It just knows 2 and 1, or 1 and 0. Okay? If you model it the other way around, what you're actually modeling is towards the absence of disease rather than the presence of disease. Or in Peter's case, he's looking at unconsciousness among fighters. If he reverses that, we're modeling towards which ones stay conscious rather than which ones stay unconscious. So that's the first conceptual bridge you've got to wrestle with. Okay, so eventually we want to create that equation, and that's something you have to become comfortable with. If you're math phobic, that's okay. You can impress your examiners by putting that in your first results page, your reference page. And remember what these things are. So who remembers what these B's are? What are the B's? Impressive. Coefficients. And that first one is a special coefficient. What's that? Constant. That's the constant, exactly. And that means nothing. It means something. But for your purposes, you don't care about it. Just make sure it's there. But in terms of interpreting what this all means, that means nothing to you. But these are the most important things, because what do they give us? Yes, when I do what with it? Almost there. I do something. I got to transform it somehow. Well, how do I get rid of this? That ln. Exactly. E to all this gives me this. Therefore, e to each of these gives me their odds ratios. Right. So ln is the natural logarithm base e. This is the probability of your outcome. In this case, the probability of having HIV, the probability of being knocked unconscious, probability of being employed, whatever your outcome measure is. And this is, what is that? What is probability divided by 1 minus probability?
The odds.
The odds, exactly. Look at you guys. Yeah, you're statisticians now. So all this is the natural logarithm of the odds. So that's what we care about, these things. And these are the presence of our explanatory variables. Okay. So that's really what we want at the end of the day, is this equation. Now remember, this equation is just a model, meaning that it is attempting to simulate the real world. It'll be good or it'll be bad. Its goodness is based upon the quality of your data. For example, we could attempt to model the presence or absence of HIV, right? Looking at the color of your hair and your height and whether or not you got your feet pedicured this week. None of which is relevant. We could make a model though, right? But it's not valid for the real world. So ultimately you are modeling or simulating the real world. The degree to which that correctness, the degree to which that is valid, comes down to the quality of the variables you have chosen and the quality of the data you have chosen to populate. And that's the conceptual gap you're going to have to discuss in your discussion. All right. And this just summarizes what I just said. Right? So some statisticians prefer pi to p, same thing, right? Probability, and this summarizes what all those things are. I stole some of these slides from an online presentation, which is why they're a little repetitive. So I just said this. You raise the coefficients to E and you get the odds ratios. And what we're looking for is an S-shaped curve. It's going to give you that automatically. It's modeling all your data towards the sigmoid curve or S-shaped curve. Again, impress your examiners by using the word sigmoid. And also impress them by showing that it's different from a linear relationship. Now, I know that Gaiath is doing a linear regression for his systematic review. Maybe some kind of meta-linear regression, right? That may not be entirely linear. It might be sigmoidal, you never know. But again, you can one of the things you can present in your results to show that you have thoroughly explored the model that you've created is this plot. So you can play with SPSS and it'll give you the plot that you create. So make sure that that y-axis, that is the probability of your event happening, and the x-axis is the change in one or more of the explanatory variables. You can do this for each of your explanatory variables. That's kind of interesting if you want to play with it some more. Let's say you find out that if you're modeling, in your case, HIV status, and you're modeling income and height and all these things, you find, oh, income, that's really fascinating. I'm really finding some interesting things here. Create this little probability map and see, in fact, if it is sigmoidally shaped. So one of the important things we looked at is tests of significance, the diagnostics, figuring out, is your model good enough? And we looked at a bunch of these things. I don't think you have to do all of them. I think you should do most of them. And there are other ones you can do too. One I didn't teach you about is something called the ACA-IK Information Criterion, the AIC. You can look that up if you like. SPSS will give you the data to look at the AIC. Other kinds of stats platforms like SAS love AIC criterion. That's their first place they go to. I didn't teach that to you because SPSS doesn't do it well, but you can do it. What the AIC does is compare each of the models that you create to its previous iteration to see if it's getting better or worse. It may not be relevant to you if you're only doing it in the forced entry method. Okay. Now there's a version of the AIC, and Gaiath will love this, called the BIC. You know what the B stands for?
Better.
Ah! Bayesian.
Oh, okay.
Ah, see?
Okay.
You guys don't need to know what that means, right? But it's a stats word that makes them very happy. So you can look that up if you care about it. I actually put another paper on the website that explains things very, very clearly, I think. How the steps of how to do logistic regression, in case my explanations are quite poor. So on this list, I wouldn't worry about this one too much, the log likelihood, because it's a little confusing. If you're not stats savvy, you may not be able to explain it well to your examiners. If you want to do it, it's actually quite powerful, and the stats people always go towards it. But these other ones are really easy to understand. SPSS gives you the output quite readily, and I showed you in the previous slides how to interpret the output. And that's more than enough for a master's degree diagnostic of your model. But if you want to go forward in this sort of technique, then you can read more about deviance scores and log ratios. So we mentioned there are 3 ways of doing a regression using SPSS: backward, forward, and simultaneous, also called forced entry, right? And if you're doing backward or forward, the most common way of doing it is using the likelihood ratio. What this means is, of these 3 methods, this is how the computer figures out whether or not to keep a variable in the model using one of these methods. The conditional method doesn't matter. It's a test it does to see if it's changed the model cohesiveness and power. Most commonly, we use the LR method. So I think, for most of you, you'll be doing either this one or this one, the backward LR or the forced entry. Forced entry is the easiest thing. That's just pouring all of the variables in and forcing the computer to figure out how much they matter. Backwards is when you start with all of your variables, you let it run and test each one in turn to see which ones fall out. I recommend that you try this. Try the backward one. and see if it horrifies you, because it may. What it may end up doing is toss everything out, and you'll freak out. Say, oh my God, I got no variables left. Oh my God, I got no thesis. Right? If that happens, do the entry method. What it probably means is you've got some data issues, and you got to go back and prune them and take out the outliers and fun stuff like that, which you should do to make it a great thesis, but you only got, like, most of you, less than a year to do this, so it's good enough. But try the backward method and see what that gives you. Okay, this is the paper I just uploaded if you want to read more about it. So, if you were, this is output from SAS, not SPSS, but the same kind of thing. And it just shows you what you're going to look at the end of the day. You're going to have the parameter, and this is the explanatory variable. This particular model only has one parameter, that's age. Sorry, bring my microphone closer to me. Since my technology is not working, I'm going to carry this around. Right? The estimate is going to be your coefficient. So again, different programs call it different things. Standard error, you know what that is, but it doesn't really matter because you don't care about that. What you care about is the p-value. That's what this means. Probability greater than chi-square. Well, that means it used a chi-square function to compute the p-value. That's all it means. So don't let that confuse you too much. So if the p-value is low, what does that mean?
Must go.
The null must go, which means it's good in this case. Sometimes p-value is low is bad for you, depending on the test you're doing, but it always means something is significant. So in this case, it is significant. And you can use this information to produce a confidence interval. SPSS will do it automatically for you. Aren't you lucky? Back when I was in grad school, we had to use SAS and do your own confidence intervals and all that stuff. Okay, so you'll see this word pop up a lot, walled. All that is a kind of test that it does to figure out its probability, its p-value. Walled is a kind of chi-square. Okay. Obviously, I'm giving you all the shortcuts here. I'm not going deep into how things are done, just how to interpret, how to read these things, because your time is short. So in this case, age is our explanatory variable. Degrees of freedom, doesn't matter, right? We've got a very, very low p-value, so we say at the alpha equals 0.05 level. Anyone not know what that means? Can we explain that? Okay, okay. So if the cutoff level of 0.05, we say that this is significant. At the cutoff of 0.01, it's significant. At the cutoff of 0.001, it's significant. It's very low. I think it's very, very significant. In fact, all the cases you'll see, they're probably really, really significant, if at all. It's very rare to find something that's only moderately or barely significant when you're doing regressions. Okay. So it's saying here the best estimate of the change in the log odds for age is 0.0285. That's what that means. What does that mean? That means for every incremental change in age, the log odds of getting your outcome increases by 0.0285. The log odds. So the e to the log odds give me the actual odds, right? And we're 95% confident that the change lies between this number and that number. This is the 95% confidence interval. Right. We can convert that as well to odds ratios. So take e to that, we get the odds ratios. So the person's odds of contracting the disease, in this case, increase 1.029 times for every year they age, every increment of that variable that goes up. So if your variable is height in centimeters, then for every increment of centimeters in height, the odd goes up this much. The computer doesn't know what these things means. It just knows the number. So how you enter the variable matters, the units that you're using. You have to remember so that when you interpret it, that's what it means. If you put the age in seconds instead of years, well, it's crazy, right? So this odds will be, for every increase in 1 second of age, it'll be 1.00000000001 change in odds. So how you code the data will matter. Obviously, years for age makes sense. There's a certain kind of human naturalness there. If you find that height in millimeters is giving you a 1.0000001 change, then recode to height in meters. That makes more sense, right? Okay, and so forth. Right. So we need to have a large number of observations in your data set. How many? It's hard to say. This particular guy says 30 is a minimum. I know your data sets well. Most of you, all of you have much more than 30, so you're fine. Okay, and you've got subset about 50 or 100?
72.
72, fantastic. Okay, we'll make it. All right, so, and there's a rule of thumb around number of observations and the number of variables. I forgot what that rule of thumb is, but it doesn't matter because you've got the variables that you've got. You've got the research question that you've decided upon, and you've got the data that you have. So this is what you have. At the end of the day, you work with what you have. Okay, so let's go through the steps of what you have to do. First thing you have to do is to clean your data. What does that mean? It means look for miscoded data. If you've got data of thousands of people, as I know Sahar does, because she has population health survey data, that's a difficult thing to do. But you can do it if you go through each variable and just rank it, right, and see at the very low end, are they all like points, are they all zeros? At the high end, if you have someone with age of 2,000, well, that's a problem, right? So there are quick and dirty things you can do to see how clean your data is. Are there any missing ones? The miscodes are very, very common, especially for public data like yours. So occasionally they have things like 1 for male, 2 for female, 3 for no response. Suddenly you've got an average sex of 2.8 or something, which makes no sense. So you've got to look for those miscodes all the time. Are all the data in numbers? Here's an example. So maybe you have the province of where you live, and it's got Ontario, Manitoba, BC. Those are text inputs. So if you go to SPSS's variable view, it'll have the variable name, and it'll also have what kind of variable is it. Is it text? Is it ordinal? Is it whatever? Don't make it text. If you can avoid that. You can recode it so that 1 equals Ontario, 2 equals Manitoba, 3 equals whatever. The reason for that is if someone has spelt Ontario differently than somebody else, then it'll see that's 2 different entries rather than the same entry. Very, very common, especially with clinical data. When you're looking at medical records and some nurses type this stuff in. Right? So if you can convert things to numbers, that's great. If you've got thousands of people to convert, well, you got to be clever. You got to search through all Ontarios, and if Ontario, then change to 1, whatever it might be. And then you go and then you do a ranking again and see if anyone didn't get searched and converted. You know what I'm talking about. Be clever, but convert. Right. Step 2. Which variables do you care about? And hopefully you guys have all figured out that this is not an adventure into letting the computer do all the work. More than 2/3 of this is you guys intellectually figure out what you want. And this is the first step where you intellectually figure out what you want. So you've got a whole host. You have got like 20 or 30 variables. You've got like 5 or 6. So we all went through this process already of figuring out which ones do we care about. We haven't done this yet, but we have to. So if, in the case of Peter's data, if I can talk about it, he's looking at, MMA fighters and whether or not they get rendered unconscious. So we don't really care about would the fighter win by decision. That's one of the variables we have. Doesn't matter. All we care about is getting conscious or not. In fact, if he won by decision, chances are he wasn't knocked out. Right? So that's an example of don't let the computer figure it out. You take that fucker out. Right? Also, like, was he on the ground wrestling? You don't care because he's not getting knocked out. He's on the ground. If he's standing up, that's what we care about. Okay? That's the kind of logic you have to apply. You have to really apply your intellect to figure out what you care about. Are they continuous or categorical? This is an obvious question. Sometimes it's not so obvious. Some things seem categorical and they should be continuous. Ordinal variables, in this case, should be treated as if they are continuous. Examples of ordinal variables. How many children do you have? How many fights have you been in? Right? How many rooms in your house? Okay? Now, they're ordinal because you can't have 1.5 rooms in your house, despite what the real estate agents tell you. That 0.5 room is just a corner in the living room. It's not another room. Right? You can't have 2.5 fights. But we treat that ordinally. We treat that rather continuously. Once you've identified your categorical variables, this is one of the first things that messes with people with logistic regression. The categorical variables are compared to each other. They're not compared to the other variables. You have to decide which level in your categorical variable is the reference category. For example, socioeconomic status. It's low, medium, and high. Right? You have to decide, am I going to compare everything to the high or everything to the low? Because at the end of the day, it's going to give you an odds ratio saying if you've got SCS of high, then it's 2 times more likely to have HIV versus the low, right? So it's versus another category. Interestingly, I would accept an argument that that should be a continuous variable because it's kind of ordinal, right? It's hard to say. I think that's one of those cases where you possibly could make it continuous because low, medium, high, that's an ordinal variable. But a purely categorical variable would be something like the province in which you live. Ontario, BC, Manitoba, whatever. So pick one as your reference. Which one would that be? I don't know. One that makes sense to you. Okay? Now, at the end of the day, when it comes to comparing things, interpreting your data, it's going to matter a lot which one is your reference category. Because maybe you find out that, in fact, province of residence does matter a lot. And someone will say, hey, if that's the case, then living in Ontario, what does that change your odds? I don't know, because that's my reference category. I know that I live in Manitoba, it's 2 times less than if I live in Ontario, but I couldn't tell you if I live in Ontario, because that's my reference category. See what I'm saying? So choose that reference cleverly. Next step. Let's go back here for a second. Right. Next step. You have to look through the univariate descriptors. What does that mean? It means you're going to process all the variables you have chosen. You're going to plot them, make histograms, figure out their averages and their median, figure out if they're normally distributed or not, are they skewed, and are the categorical variables unbalanced. What does that mean? Let's say we're looking at province we should live again, right? You've got 100 people in your data set. 95 live in Ontario, 5 live in Quebec. No one lives anywhere else. Does it make any sense to keep those other categories open? It doesn't. In fact, that's really going to mess up the stats. If you've got a category or with a level that's underpopulated, that kind of skews the computer into thinking it's significant when it isn't. Right? So think of it like a chi-square. If you remember, when you do chi-square, no cell can have fewer than 5 elements in it. I don't know if you remember that. So as a rule of thumb, think about 5 as your base. Right? No levels have fewer than 5 things in there. Probably a lot more than 5. So one of the things you're looking at when you're doing univariate descriptors is an opportunity to collapse levels. So the example I just gave you with province of residence, if you've got 95 in Ontario and 5 in Quebec, maybe change that category to Quebec versus Ontario. Don't call it province. Okay? Or take it out entirely because it's not really relevant. Or if you're looking at age group as a categorical variable, and looking at 0 to 15, 15 to 30, 30 to 40, and 40 up, and you find that most people are 40 up and 0 to 15 and nothing in between, collapse them. And so now you're looking at 0 to 40 and 40 up. Okay? So you've got to be intellectually aware about the nature of your variables to recode them appropriately. Now, collapsing and recoding is also a bit problematic because you're kind of forcing relevance. The cutoffs that you choose must be defensible intellectually. One way to defend them is to say, well, this is the data that we have, and they're clustered in this way. So if it's a continuous variable, and let's say you plot your age variable, and you find it's plot like this, bimodally. Like that. So there's a whole bunch of really young and a whole bunch that are really old. It kind of makes sense to make it a dichotomous variable, saying yes or no, young versus old. Okay. That's defensible, that sort of thing. So you have to have a good grip of what your variables look like. Spend a good few days poring over them. And especially see if you have to recode any of them or transform them. Transforming is dangerous. Transforming is when we maybe take the logarithm of the age or something like that. And the reason we do that is if we have a lot of outliers, if you take the logarithm of some of the outliers, suddenly it creates a better shaped variable. And the computer likes that more. So do consider it. Step 6. You have to explore the bivariate relationships. That means for each of your variables, figure out how well it likes your outcome. If your outcome is, again, whether or not you have HIV, figure out on its own whether or not there's a relationship between age and HIV, or the province in which you live and HIV, and so forth. Why? A couple of reasons. One is, if it's already strongly related, that's great. It means you're going to try to figure out now, when you do the regression, if these other factors are going to influence that relationship. And that's an interesting thing to talk about at the end of all of this. The second reason is, if it's not at all related, you may want to consider dumping that variable. Now, do I want more variables or fewer variables? What do you think?
Depends.
Depends? That's a good answer.
Fewer.
Sure.
Most parsimonious.
We like parsimonious. Yeah, exactly. So statisticians, we like fewer because it's prettier. But really, there's no other reason for that. You know? So it's also easier to talk about. I could, like I said earlier, I could put everything I know into this model and get as tight a model as I can. That doesn't really tell me what I want to know. I always go back to figure out, what do I want to know? I want to know which set of variables can I intervene policy with, for example, to affect my outcome. I can't really affect whether or not you went to get a pedicure or how long your toe was, or all these random things. So why is that even in there? Okay, so that's an intellectual question. I haven't got the answer for you. However, if you find in your unadjusted univariable bivariable relationship complete no association, think about whether or not it makes sense to take that variable out entirely, unless it's important for the story that you're telling. Okay. Now, in the case of Peter, for example, he hasn't got that many variables, so we'll probably keep it in. In your case, you got lots of variables. Probably won't take it out, unless it's telling an important story. All right? So what you're going to do here is, for the continuous variables, use a t-test to figure out if the mean age for those who have HIV is different from the mean age for those that don't have HIV. That's how we do the univariate test, bivariate testing. For the categorical variables, use chi-square or an odds ratio by itself. Doesn't matter. Something that measures an association to see unadjustedly what the relationship is. That's the word we use, unadjusted. Okay. Next step. This is the thing that we covered last time that some of you may have missed. Test for multicollinearity. There are a few ways of doing this. The formal way is to compute something called the VIF, but that's difficult, and you don't really need to. I would argue just make a correlation matrix, where you take all of your variables that can correlate, i.e. all of the continuous ones, and correlate them against each other, and look for high correlation. If something is really highly correlated, let's say 0.8 or above, let's say, okay, what do you think I do? If they're really high correlated, what should I do? What do you suspect if two things are highly correlated?
We have to take one of them out.
Probably. I would say so, probably. Again, this is an intellectual choice. It's not an automatic choice. So you may find you have two variables that are measuring exactly the same thing. Height in centimeters and height in feet. That happens all the time. Right? Weight in kilograms, weight in pounds. Or maybe the make of my car and the length of my commute to work. The faster the car, the shorter the commute, whatever it might be. You know? So you're actually measuring the same thing, and that's really going to mess up your results. So that's where your intellect comes in again and say, those are correlated because they're exactly the same thing. One can go. Which one goes? That depends on what your choice is. Now, if they're not measuring the same thing, we have another problem. We have two things that may be correlated because there's something underneath that joins them. Maybe they're both so really well tied to the outcome that they're following along in lock and step. In that case, we have to consider that perhaps they're interaction terms. We talked about interaction terms last time. We're going to deal with that. But the easiest thing is a correlation matrix. Now, I would say that if they're not well correlated, but moderately correlated, like a 0.4 or 0.5 or something, you should still explore them for interaction. Guys are being very uncomfortable for some reason.
No. Just trying to apply it to my own.
All right. All right. So if you were doing a multiple linear regression, this would be the most horrifying thing for you, because this is the thing that really screws up a lot of multiple linear regressions. For logistic, it's not that big a deal. It's a big deal, but not as big a deal as it is in linear regression. All right. So in your correlation matrix, see which ones are somewhat related to each other, because that's important for the next step, which is to test for confounding interaction. Which ones do you test for confounding interaction? Well, first of all, you've got your correlation matrix. You're going to test those. The confounding is harder. So the confounding, again, requires your intellect. You're going to figure out which ones are likely confounders. by looking at the question that you're asking. Does it make sense that SES is a confounder for both marital status and education? Absolutely it does. The wealthier you are, probably you're likely to be married at a young age and probably you've got better education, right? So that's something you're going to test. You could test everything. If you've got a small enough data set, you could test everything. To do so, you're going to have to identify what I call the primary explanatory variable. So if you're on a fishing expedition, as some of you are, that's fine. You know, most master's programs are fishing expeditions. Say, which factors are predictive of HIV status? I don't know, let's find out. Right? That's a fishing expedition. But you probably, wink, wink, have an idea around which one probably is the most important one. One or two. Hopefully it's just one. In your case, maybe it's women's education, right? In Peter's case, maybe it's the number of fights is the thing that's most likely, the thing we care about the most in terms of deciding the outcome, right? In Lena's case, maybe it's the program of study that's most predictive of whether or not the people are employed. So that's what we care about the most. We're going to test the other variables against that primary explanatory variable. So as we covered last time, we're going to add them and take them out to see how much the model changes. And if the model changes by more than 10%, according to the rules I gave you last week, we say that that thing is probably a confounder. What does that mean if it's a confounder? What does that mean for us? Well, it means that if you're doing a backwards selection process, the computer wants to take out variables. You can't let it take out the confounder. If you're doing a forced entry process, it doesn't really matter because they're all going to stay in. That's all this really means, really. So that's why if you're doing forced entry, it probably doesn't matter that much. However, when it comes to your discussion and defending your thesis, it's really useful if you've identified your confounders. You can talk about them and maybe do some sub-analyses where you take them out and keep them in and show their relationship to the other variables. Right? If you're doing a backward selection, though, absolutely you have to identify them to force them back in again. It's weird, though, isn't it? Like, you got to force it in because of a confounder. Yeah, but, and the reason for that is regression, by its very nature, takes care of confounding because everything's held constant. So if it's not in there, it can't take care of it. That's the logic, really, as your examiner will ask. Okay. Step 9. Now you're ready to actually run the regression. And you have to decide which one you want. Forwards, backwards, or whatever. And again, I say I recommend backwards, LR, or forced entry. Try them both. Try forced entry first. And see what I feel so weird saying, try forced entry. Let's call it simultaneous entry instead. That sounds better. Let's try simultaneous entry. But backwards is fun. That sounds weird too. When you're entering your variables for your regression, right, you're going to select all the ones you want from the left and enter them to the appropriate box. When it comes to, for your categorical variables, you have to tell SPS is categorical, or else it will not know. It's a dumb computer. It doesn't know what you don't tell it. And it'll ask you, what kind of categorical variable is it? You can choose deviation or indicator. Choose indicator, unless you really want deviation. If you want deviation, come talk to me about why you want deviation. But indicator is what you want. What indicator means is it's going to take one level and compare everything to it. What deviation means is going to take a central estimate and compare that to the central estimate. Difficult to interpret. Why make your life difficult? Okay. Choose indicator. And you press run and see what happens. Hopefully it'll work. It may not work the first time. You may freak out. Why is that working? I keep crashing. I understand. It's okay. Take a deep breath. You gotta make some changes. It's okay. Okay. Next thing you're going to do is run your diagnostics. As I mentioned, you can run the Aka-Ike information criterion or the Bayesian information criterion. These things I didn't teach you how to do. You can look those up and impress people a lot. Or you can run these simple ones. And the ones I recommend you do all of them because they're easy and it's impressive. And you can be really confident when you go to your defense because you've done all this and you convince yourself that my model is strong, damn it. What all these tell us is how well the variation in your variables predict the variation in your outcome. That's all it tells us. It doesn't know the real world. It doesn't know whether or not age is a predictor for HIV status. All it knows is its own variables. So the big ones here, I mean, the R squared, we kind of know what that is from your basic stats class. SPSS will give you 2 modified R squares. Look at this, the Snell version. Again, in last year's presentation, I showed that. Hosmer-Lemeshow is the go-to one. Hosmer limit show goodness of fit test tells us how well these variables fit together. It's kind of the standard way of doing things for those of us who aren't really like semi-autistic statistics nerds. Just go to that one because we understand that one. And lastly, the classification plot is a nice thing to talk about in defense because it's visual. You can just show, is it U-shaped or not? You want a nice U-shaped curve. If there are things clustered in the middle, what do? You remember what we do? We have to prune. You have to take out some observations. How do we figure that out? We look at the case-wise listings. So the case-wise listings will show us the z-scores of the residuals. The residuals is, for lack of a better term, what's left over after you run the model. And each variable has its own residual. And depending upon where you set your sensitivity for outliers, and you can set that when you run your regression, it'll be automatically set for 2.58, which is like a 95%, 99% outlier. Okay? So anything beyond that it will identify as being problematic. You'll probably get, on a good model, 1 or 2 or 3 outliers. If you got like 5 or 6 or 10 or 20, then you got issues. And what you can do about that is take them out. Just delete those fuckers. And delete them and also keep them in a separate data set. Right? Keep them in a separate data set. You can run all kinds of diagnostics on that separate data set. Say, oh, my outliers, their average age is like 95, right? Or they're all like transsexual men or something. I don't know what it might be. So you can learn some interesting things about the ones you take out. And that really justifies your decision for taking them out. You can show, these are different from these people. They don't belong here. Cool. Okay. Next step, interpret your findings. This is the fun part. Also the difficult part. Everything we've done so far is kind of mechanical. You can just go, 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 go. This is the part that you write your discussion about. Right, so you're going to report your odds ratios and your confidence intervals and say for every incremental change in age, my odds of HIV go up by this much, and every incremental change in SES, my odds goes up by this much, and so forth, blah, right? Then you can say these variables here went from an unadjusted p-value of this to an adjusted p-value of that, showing that in the presence of these other factors, their role either diminished or was enhanced. That's the insight we take out of this. You got to make sure that your interaction terms have been forced in, okay? And you don't interpret those necessarily. You can. So let's say you find an interaction term where age is interacting with sex. So you're showing that as age increases, then the way in which sex predicts HIV status flips. That's what the interaction term means. Then you can explore that in your discussion as well. You can graph the two. You can graph in the presence of high age, here is the probability relationship with sex. In the presence of low age, here's a probability relationship with sex, or vice versa, right? And that's a fun thing to do in your discussion. It really shows that you are understanding your data well and exploring it appropriately. Also, phrase things accordingly. There's a strong temptation among students to talk about causation. We are not measuring causation here. We're measuring, at the best, association, sometimes correlation. So we can say things like, age is associated with HIV status, increasing age associated with HIV status in the presence of increased education. Never say cause, right? I mean, in a defense scenario, you'll probably get away with it. But as a stickler for detail, when it comes time to publish, that's a bad thing to do. So never say cause unless you're running a randomized control trial. Okay. Defend your thesis and graduate. That's the last thing you're going to do. I think that's the last slide there. Pretty thorough, right? Any questions? Pretty clear? Yes.
For the test for normality, I know there's KS, Shapiro-Wilk, and then even SAS has like Anderson-Darling.
Yeah.
I'm wondering what to use.
I like the Kolmogorov-Smirnov test, if I understand it well. So it doesn't really matter.
Okay. Is that one like less strict than the Shapiro-Wilk one?
No.
No? Okay.
In fact, it's about the same, I think. But they're all kind of the same thing. What are you testing? What variable?
I just ran some sample ones and they were giving me different p-values.
Okay.
I think KS said it was significant. Sorry, it was normal, and then Shapiro-Wilk said it wasn't.
Can you graph it and look at it visually?
Yeah.
Yeah. So in that case like that, I would choose whatever I want,
Okay.
and I would justify with a visual appraisal. Frankly, it doesn't really matter if it's normal or not, as long as there are no extreme outliers and no extreme skewness. If it's vaguely normal, it's good enough. All right.
Okay.
So, if it was a linear regression, it wouldn't matter. But for this, what we care about is, are there cases in which something weird is happening? You can prune those out at the end. And we also care about if it's bimodally distributed or trimodally. So visually appraise and see what happens. Oh, wow, everyone's clear on shape. Great. Have we started?
Yeah.
Right on. Okay.
Will we email you? I will be emailing you questions.
This is what I'm scared of. All right on, cool. Well, that's all. Hey, hopefully it works, And if we ever do this again, let me know. Maybe we can do something on another topic. I don't know.